Okay. Yeah. 278. Let's go. First, 278. What is this? Two horizontal discs rotate freely about a vertical axis passing through their centers. The moment of inertia of the disc related to the axis are equal to I1 and I2. Negative systems are equal to omega 1 over 2. And then the upper disc fell on the lower one before. Okay, both discs begin rotating. Sorry. Two horizontal discs rotate freely about a vertical axis passing through the centers. Moment of inertia given, angular velocity is given. Upper disc fell on the lower one. Both disks began rotating, okay, after some time as a single whole, okay, due to the friction. Find the steady state angular velocity of the disks. So just consider of angular momentum because what else can you do? And the work performed by the friction forces in the process, right? Yeah, angular momentum conservation works because hinge force is, well, zero. One of the disks fell, so yeah, sure, no big deal, right? So when it fell, the yeah, like gravity didn't actually do much because it was a small time. So angular momentum conservation, what does that tell us? That just tells us that I1 plus I2 times omega is equal to omega 1 I1 plus omega 2 I2. That's actually, yeah, it's so simple. So you got the thing, right? That's the angular momentum. So the angular rotation velocity. So A was just a piece of cake. Of course, like a vector, and I2 omega 2 vector. Concentric disk, I suppose. I mean, okay, con x, whatever. This with the same axis or verticals, right? The work performed by friction forces in this process. What? Just the heat lost, right? Yeah, or you just the change kinetic energy because what else is doing work? Hinge forces, nah, and no other work is being done. So just that much, right? So there you go. Yeah, you got like final L is just this thing I1 omega 1 plus I2 omega 2. That thing squared upon 2 I1 plus I2, right? That's final kinetic energy. And the initial kinetic energy was just so I1 omega 1 squared upon 2 and then I2 omega squared upon 2. So the difference of these is just the work done, right? I will just leave it like that because I don't want to actually simplify this, right? This is good enough. Yeah, we don't care about this. This minus that. That's the work done by the kinetic. Okay, I should say the negative of that. Yeah, well, the negative of that. Really. Also, I mean, sure, friction always does just negative work. So we should make this negative instead of saying just the heat loss, right? Or the kinetic energy loss. We will say this is the work done. Next, 279. Okay, a small disk and a thin uniform rod of length L whose mass is this many times greater than the mass of the disk lie on a smooth horizontal plane. Rod of length L whose any figure, okay, nothing is given. Fine. Thin uniform rod of length L. So rod mass eta times that of the mass of disk. Okay, so this is like eta times small m, and you got this disk. Smooth horizontal plane. So this is the paper, plane of paper is just a smooth horizontal plane, right? You got this disk, mass m. This is length L, whatever. Disk is sent in motion in a horizontal direction perpendicular to, I thought that this thing, with velocity v, after which it elastically collides with the end of the rod. Find the velocity of the disk and the angular velocity of the rod after the collision. At what value of eta will the velocity of the disk after the collision be equal to 0? Reverse its direction. Wait, what? Okay, so first it can be 0 and second it can also reverse its direction. Oh, okay, understandable. Right. So first of all, what do you want? Um, yeah, like just want the velocity of center of mass and this guy's velocity and all that stuff is a function of eta, right? Okay. So this is a distance, I don't know, x. Yeah, if I want to do this, I want to do this for the general thing. So the angular momentum with respect to this point of this complete thing. It's just moving with v naught, right? So it's just going to be what? M v naught x. Okay, that is our, okay, that's the angular momentum. Uh, right, and this is going to be equal to the final angular momentum when it, right, does that. Oh, it's, it's kind of complicated. Okay, there's a bit of problem with this thing because we will not, oh god, it's going to be some complicated thing going on. Fine, not so big a problem. We can do it, right? We can do it. So, using momentum and everything, right? Okay. Or you know what? No, let's just say m times v is momentum. So v is just the like dummy thing. Okay. So we want angular momentum. This center of mass angular momentum about this thing is just 0. We just need to go for the rotational one. Right. So it's like ml squared upon 3. Or you could just go with r. So we'll just say this complete thing is r. So you got mr squared upon 3, or I should say eta mr squared upon 3. That's our inertia. And then this times omega. And it's in this, yeah. And then you got, just wait a second, omega. Oh, and by the way, what is omega? Do we know that? Using momentum and everything, you can actually figure that out, right? Okay. Oh no, it's gonna get complicated like this because what you want is like the energy losses to be 0, right? Yeah, yeah, that's the thing. So you want your energy losses to be 0. So, okay, this is not the equation that you'll use for momentum. Instead, you just say, okay, the momentum will be acting on this thing like P and then on this guy P like this, okay? So for this guy, the change kind of just half M, you got this thing, P naught minus P upon M. Yeah, minus P upon M, all of that squared minus half M V naught squared, right? That's the change kind of energy. What is this going to be? It's going to be like half M and then subtract, so just negative P upon M, then add, so 2V naught minus P upon M. There we go, that's the thing. So that's the change in energy, which is just negative P upon 2 times of 2V naught minus P upon M. Right, think about it. It's just like negative PV naught. You got plus P squared upon 2M. That's the change in energy. Cool. Because of this, just this guy. And you also want because of this guy. What's happening? Okay. So how much is that going to be? So it has omega is equal to, or just say L. L, so angular momentum is just equal to P times of X, right? So L squared upon 2I. So it's going to be Px squared. So you got P squared X squared upon 2 inertia, which is just 2ml squared. Okay, R squared upon 3. So there we go. That's the thing. And also the kinetic energy, right? So it's going to be like that. P squared upon 2. P squared upon 2 times of E time, I would say. That looks good. Okay. So P cancels from everywhere. Yeah, and multiply by M. Actually 2M, you know. So, or you know what? 2E time, nah, okay, just PM. Cool. So it's gonna be what? Negative. Or you know what? Nah, okay, just leave it like X. We don't want to get more complicated than that. So it's just negative 2mv naught plus P is equal to 3px squared upon 2r squared, and then plus, that's gone, right? Okay, so just P upon eta. Cool, that's the thing. Perfect, and you just got the value of P in this case, right? So P times of, yeah, um, this thing, okay, that's supposed to be that. So like 1 minus, and eta is this like bigger than 1, smaller than 1, we don't know. Just the moment, like of course momentum has to be positive. This has to be positive. How else is gonna work? Um, but when can this be positive all the time? Okay. I get what went wrong. It should be this thing plus that thing that's equal to 0. Yeah, that makes more sense. So this is the thing. right? So now what do we have? Just p, and then you got all of this. So 1 plus 1 upon eta plus 3x squared upon 2r squared is equal to what? Like 2mv naught. So we got momentum. Did we have to find this? Maybe, maybe not. What was the thing once again? Okay, at what value of eta will the, so yeah, right. And also the angular velocity. So you have to figure out the momentum, otherwise there's no escaping all those equations, right? We have to do this thing. Okay, now that we have this, let's do the thing. Wow, it's gonna get very complicated actually. Fine. First of all, what is the velocity? Um, right. So v is just equal to v naught minus p upon m, which is this thing. Okay, it's like 2 v naught upon all that, right? So it just v naught times 1 minus 2 upon all of this thing. So 1 plus 1 upon eta plus 3x squared upon 2r squared, right? Exactly. Perfect. And do you want to simplify this thing? Maybe. I don't think that's going to be a good thing to do, but whatever. Nah, just leave it like that. Who cares? So that's our v. And what else do you want? You want omega. So omega is just p times of x upon the inertia. It's like just px upon ml squared upon 3, right? Yeah. So it's like 3px upon ml squared. R squared, sorry. See, you have to figure out what that thing is like. Okay, p, just substitute that over there, right? All of this, 2m not upon, right? And you want 3x upon mr squared of this guy. Okay. Wow. It's gonna take forever. We got 6, and then m cancels, I guess. 6x v naught upon r squared. Is that right or not? Yeah, that's supposed to be correct. These are all just pure numbers. So you got, yeah, looks good. And then you want this thing, 1 upon all that, right? So let's put this -1. You got all of this, 1 plus 1 upon eta plus 3x squared upon 2r squared to the power of -1. Similarly, p, you can just write it like this. So got this. There we go. This thing power -1. Nice generalization, isn't it? So you got thing, you got p, you also got v, and you got omega. You know what? Since we're writing like that everywhere, so might as well just do it over here as well. So this power of -1. Cool. Yeah, whatever. Just paste this. All of it is power of -1. Cool. Next question. Next. 280. Oh, okay. We don't actually answer the thing yet because, right, we actually have to figure out what this thing is, right? Okay. So, what do you want? You want the velocity of the disk and the angular velocity of the rod after the collision. So we got that. We just put x is equal to 1 because it's like at r, and r equal to l upon 2 and get the thing done, right? So, oh, x is not equal to 1, x is the distance, so x equal to r. That's better. Sure. So once you do that, you just get like 6 x v naught, okay, all that stuff. You can figure that out. So for v naught, you got v naught times, so for v, you just have this thing 1 minus 2. First of all, just figure out what this value actually is, because, right, just 1 plus 1 upon eta, and then just once, like plus 3 upon 2, so you're gonna have 5 upon 2, right? So, right, 5 eta plus 2 upon 2 eta upon negative 1, which is like 2 eta upon 2 plus 5 eta. That is this thing. Okay. So when you do this thing times that. So this, just keep that in mind. So your V, oh, okay, first of all, your omega. Omega will just be this times that, which is, and okay, this cancels, which is like 6 upon R. And then you got V naught and this. So, once again, R is just L upon 2. So you can write select 12 upon that. That makes sense. So 12 V naught upon L, and then you got this thing. So 2 eta upon 2 plus 5 eta. And then what is our V value? Will be this thing, which is V naught times 1 minus 2 times of all of this, which is like 4 eta upon 2 plus 5 eta. Isn't that right? So it's going to be what? V naught, boom, that goes away, just 2 plus eta upon 2 plus 5 eta. This is the thing. Perfect. So you got the thing. And similarly for this guy, you could just write it like what? 24 eta upon 2 plus 5 eta, and then you got V1 upon L. Next question. Finally, okay, 280. 280 is a stationary platform P which can rotate freely about a vertical axis 1.72 supports, okay, like this, supports a motor M and balance weight N. So this is a motor M and weight N. The moment of inertia of platform with the motor and the balance weight relative to the x-axis is equal to I. Relative to which axis? This axis? Oh, my mouse is still not working. Just wait a second. And yeah, okay, that's a quick fix. So stationary platform P, which can rotate freely about a vertical axis, supports a motor and a balance weight N. Right. The moment of inertia of the platform with the motor and the balance weight related to this axis is equal to I. Total inertia of this whole thing is just I. Right. A light frame is fixed to the motor's shaft. Light frame. What? Okay. With a uniform sphere, so this thing, right? EB dash, that's our frame. Okay. Uniform sphere A rotating freely with an angular velocity omega naught about a shaft PB dash. Okay. Coinciding with the axis OO dash. All right. The moment of inertia of the sphere related to the rotation axis is equal to I naught. The work performed by the motor in turning the shaft PB dash through 90 degree and through 180 degree. What? You want BB dash to be turned? Something's not right. So you want to turn that? Oh, that's weird. Okay, so this like this motor. Oh, okay, that's what's happening, huh? I get it. I get it. One thing we know is like all the things that these yeah, all of the energy just done by motor. Okay, we know that one. And angular momentum conservation. Okay, that's something that you can do. So perfect, perfect. I would say the work performed by the motor in turning the shaft PB dash through 90 degree and through 180 degree. So you want the work performed? Yeah, it can be done. So you just want the change in kinetic energy. What else? And the moment of external forces which maintains the axis of the arrangement in the vertical position after the motor turns the shaft. Wow. Made of external forces. What external forces? Which maintains the axis of rotation, sorry, axis of the arrangement in the vertical position. So you mean axis O dash, right? That is always vertical. Okay, I get it. Fine, 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 fine. right? So yeah, okay, that makes sense. Which turns the shaft BB dash to 90 degree, right? We know that's going to happen. Cool. And when that happens, right, what is the torque due to the external forces? Basically, that's what it's asking. And also only those forces which like prevent the axis of arrangement to go. So axis, yeah, just O dash. So what keeps this O dash vertical? So those are just external forces, right? And what's the torque use of those external forces? That's basically what they're asking. Okay, so basically it's like a gyroscope. Isn't that right? Of course it is. Um, but a pretty complicated one, right? Okay, it's probably got this thing in angular interpretation because there's really no. Are we sure there's no external torques? I mean, okay, this is complicated. Are we sure there are no external torques? Um, with respect to okay, what we could say is like just make our system only this platform and all of the things on it, right? Forget about the axle because that has things on it which you don't want to consider, all right? So this little part, yeah, don't consider that. And there's like gravity and everything, but because of that, there's no actually actual torque because M and N have the same mass, and this is like complete symmetric about its axis. So center of mass definitely lies on the axis. So yeah, you can just get rid of all of that. Perfect. Um, so there is no torque because of gravity. There is no torque on the system because of external forces, because there's only like hinge forces which are external, and those don't do anything exactly. So you can just do angular momentum conservation for that thing, assuming that the axis is actually frictionless or something like that, right? I mean, even if it was having friction, no, okay, that's a different thing altogether, right? Then you can't do because there is a torque, of course. Wow, it's getting complicated. Yeah, you have to do it. I don't I don't know where to start. So first of all, you got the angular momentum because of this guy's like pointing up. Okay. Oh no, okay. The axis is like wait a second. It's rotating about that, right? Oh, and the motor is actually turning this in that direction. Fine. So when it's completely along 90 degree, this sphere has omega in this direction because of the platform, and also it's actually going around BB dash. So there's that omega. That makes sense. Uh, yeah, its angular momentum is like in that direction and in that direction. And oh god. All right, okay, that explains it. Actually, does explain it. Just want to torque in the this direction and wow, very complicated. How do we do this thing? I get it. Like I mean, they just want a perfect gyroscope, but it is complicated, isn't it? There's work done by him, and then yeah, understandable. We can figure out what the angular momentum of this complete thing is, and then conserve it and everything. But then to figure out the forces, how would you do that? We just want the external torque. We don't actually want the forces, right? Oh, oh yeah. We just want. Okay, fine. Then it's actually. I think it might just be doable. Who knows? So gravity effects, just forget those, right? Because this cardboard sheet, this doesn't actually matter. I mean, yeah, it's just a light frame, and then this sphere is what matters, doesn't it? And because it's symmetric, it's like spherical, of course. Gravity doesn't do anything. So just angular momentum conservation. Sure. Anything else given to us about uniform motion or something? So initially it was omega naught about shaft PB dash, and this platform, it was not moving, right? Stationary platform, and now it's gonna move. Cool. Oh god, this is so weird. You can definitely do the work. You want the torque somehow, and the torque on what exactly? On the whole system, of course. Okay, on the whole system, including the axle, but then the axle's angular doesn't need to change. Oh god. I don't get it. Why is B not zero already? Why are they asking us what it is going to be? Moment of external forces which maintain the axis of the arrangement in the vertical position after the motor turns the shaft BB dash to 90 degree. Yes, it's gonna turn, and then so just taking this as a system, sure, it would have made perfect sense why you would want the force. But when it's not the case, then how can you do that, right? How can you figure out the torque? It's gonna be zero, right? It's going to be zero. Think about it. The axle, it has zero angular momentum really because these parts are not moving. This complete thing, this guy's angular momentum is completely, you know, constant because taking this as a system, there is really no torque on this thing. All the hinge forces, they produce no torque at all. So this guy's angular momentum is also constant. So using T equal to dl upon dt, this should give us zero. Um, but what that means is like, okay, these forces actually they don't produce a torque at all from the external. Yeah, the ground doesn't give any torque on this thing. That's what it's saying. So B is just zero. What do you mean by external forces? No, I don't understand what they mean by external forces. There are no external forces producing torque. I think they might mean the force due to, due to the motor. But that's not external. How can that be external? Right? Oh God. Something is going wrong, of course. It makes vertical. Is there any external force? Wow, it's not good. Not good. God, how do I do this? Okay, okay. What we could say is that suppose there was an external force that was doing. Okay, that might be the thing. So your angular momentum could be changing, which is yeah. So that's not happening in actuality. But suppose there was an external force, then it would change, right? Of course, and then you can just do dl upon dt to get the thing done. And oh yeah, okay, that makes sense. When it's 90-degree like this, it's going okay, okay. Then it's a proper gyroscope. Ah, of course. Oh, this was so not good. Um, right, first we'll have to figure out what the angular momentum is. So for the sphere, it's just L equal to I omega. I know, I have said this countless times that for 3D objects, you should not do that. But we already showed that this actually works for axisymmetric cases. For M and N, we don't know what's exactly happening. So the inertia of this platform along with these motors, that is supposed to be like that is I. So is I omega really the angular momentum or what? I mean, it's also axisymmetric if you really think about it. Except that, okay, yeah, this is not completely rotationally symmetric, but then it's symmetric about this axis in a way. So you could say that L equal to I omega. I think so. Yeah, it might just work. Like, think about it. This guy is, oh God. Sure, just think about it like that. L equal to I omega for this as well. Okay, does that make sense? Just write down some stuff. So the angular velocity of this platform, we'll call that as omega, and angular velocity of this thing, right, about bb dash. Okay, so about bb dash, that will be omega dash, both vectors. So bb dash by itself has omega vector about oo dash, right? So the total angular velocity of this thing is going to be omega vector plus omega dash vector. We already proved that once. Okay. Okay, cool. So what do we get? We just get the total angular momentum is equal to the inertia of this whole thing, of the platform and everything included, and then plus I naught times omega vector and plus I naught omega dash vector, right? Okay, because yeah, I mean along any diameter is going to be it's going to be I naught, so we don't have to worry about that. Right. So this should actually remain constant. Omega vector is completely along the k hat. Omega dash vector, it can change actually. Fortunate. Yeah, that doesn't look good. It should not change, but then how does that even work? There can only be omega. Yeah, like there can only be one direction where omega dash can be pointing. Otherwise, this is not completely the k direction. It's gonna not obey our angular momentum conservation. So yeah, that doesn't look good. Yeah. Right, there must be torques doing some stuff. Oh god. There must be a torque that the axis actually puts. But no, it doesn't make any sense. Any kind of hinge force that we put, it will not produce any torque. So how can the axis do it? Oh, it's not making sense, right? And it's rotating freely about, so there's like no friction or whatever. Ah, it's not making sense. The only forces other than gravity and things are just from the hinge. Okay, from the axis. And we have always assumed everywhere that those produce no torque. Okay, for let's just think about a normal gyroscope, not this crazy one. So you got this gyroscope and it's rotating like that. We know its angular momentum is not constant, it's changing. What is providing this torque? Uh, and is this freely rotating about the axis or not? So the torque is being provided by the ground, of course, right? So this is connected to the ground in a way, and that is providing the torque. Sure, sure, of course. And wow, okay, that's very weird. The torque is there. What? There is a torque, but the hinge forces are zero. Then how can there be a torque on this complete system? How can there be a torque? I don't understand what's happening. No, it doesn't make sense. How can there be a torque? I just set it free. This is going to press. Okay, yeah, it's angular is going to change, I guess, because oh, there is a torque, of course. Ah, okay, it's not like this case. There is a torque because of gravity, right? And that's the way that you get the thing for gyroscope, right? There is no torque from the surrounding. It is just angular conservation, or okay, T equal to IF. That equation. Similarly, for this thing, you can do the same, but yeah, there's no torque. There is no torque. Okay, but that would just mean like omega dash can not, right? So if I just leave it like that, it will never actually, yeah, like it will never, in fact, uh, want to go in a direction like this. Oh wow, that's not good. Right, it will never do that. It will just stay vertical as it is. Of course. Why would it do this thing? Right? That does make sense. Sure, it does. And if you think about it, even if this, right, okay, that makes sense. Like, what if your omega dash was not initially vertical? It would be a bit horizontal. It's gonna become vertical, right? Where have I seen this? I think I've seen this somewhere. Just cannot remember that. Huh. What about, it's like, okay, maybe M has something inside of it that can have a changing angular momentum, right? That would be one explanation for this thing, right? Yeah. Oh God. The only force on M are like friction and the axial putting forces. So when M tries to make this happen, what exactly happens in real life? Does this become like horizontal or not? Wow, this is complicated. Right, I have no idea. I think we need to do some research before doing this one. Right then. So I'll see you in the next video. Bye.